Hi, welcome to this video on using Python to enter the Kaggle competition on bike sharing. So we're here in Domino and we're going to start with this project that I've created called bike sharing. You will eventually take this project and fork this off so that you have a copy of your own, an individual copy. I'm going to go into this project and we're going to check out the overview. So here we're going to be competing in Kaggle's bike sharing competition. The data is available from Kaggle. We're going to have this starter code, which is Python code that is in this Jupyter notebook, and we're going to get a chance to see how to use Python to fit two machine learning algorithms. One is called a random forest, the other is called a boosted trees model. You can download the training and testing sets if you want local copies of them from this link, but we've already got them here in the files section. That's the training CSV, or the train CSV and the test CSV here. You're going to want to grab local copies of those two files because you're going to want to take a look at those in Tableau first and see which features you think from a visualization perspective might be good predictors. Then in this video we're going to grab a hold of this starter code in Python that will build some rudimentary predictive models, and then later, once you have seen what this code does, you might take a crack at extending it, repurposing parts of the starter code to include additional features beyond the ones that the starter code includes in these rudimentary models. You're going to want to do some readings at the links provided throughout the starter code. That'll give you a sense for how these two machine learning algorithms work. These are two of the arguably best machine learning algorithms out there for competing in these competitions, and you might want to do some other things beyond just including additional features in these models to come up with a final prediction that you're going to submit to Kaggle. And while this competition I believe is closed, you can still get a hypothetical rank on the leaderboard, and we'll award a prize in class. Okay, so I'm going to now go into Files, and I'm going to click on the starter code, the Python code, and we're going to go ahead and launch a notebook. And Domino is setting up a virtual machine on AWS for us right now. And here we go. Here's the Jupyter notebook. Okay, so the following code is written in Python 3.6, and maybe if we go back here and we just take a look at settings for this project, we can take a look at here, hardware and environment. The environment we're working with here is an environment where before we were running some R code, which was version 3.4.1. Now we're working with Python 3.6, and that's important because there's a 2.7 version of Python that's also quite popular out there, and if you look at web resources and do Google searches, you'll want to be sure that you're working with the syntax that goes with the more recent version of Python. Okay, so we're back here in this starter code, and maybe I should just start with a quick Google search on what is Python. And we come to the welcome to python.org page, and this is the little symbol for Python. And just a quick piece of background on Python and where does the name come from. Some people think that that refers to a snake, and that's not true. The founder or the inventor of Python was watching Monty Python at the time, or reading published scripts, and that's where the name of the language comes from. If you've ever seen The Life of Brian or one of those movies, that's who they're talking about here. Okay, it's sort of a playful name. We're going to import some packages here that we're going to need to be able to do this machine learning on the data set, on the bike sharing data set. The four main packages for doing that are the NumPy package, the Pandas package, the scikit-learn package, which is abbreviated sklearn, and the XGBoost package. We're going to import some other packages here. These are just plotting packages. And one of the things that when you import these packages into Python, you can do is you've got this choice to name an abbreviation, so that you don't have to keep writing this out below. Python is a little bit different in R in that you have to precede the name of the function with the package that it comes from. So we'll set up these little abbreviations. So pandas becomes PD, so that when we go down here and we look for the function that reads in a CSV, we can just write PD instead of pandas, pd.read CSV, and then put the name of the file on the inside of that function, and that will read in the function. And unlike R, we're going to use the equal sign, although you can use the equal sign in R, whereas you typically saw the arrow as the assignment syntax. We're going to use equal sign in Python. That's really the only choice. Okay, and from the scikit-learn package, we're going to go into a library called cross-validation, and in particular a function called train test split, and so on with some of these. This is just a way to drill down into these packages and just grab certain libraries within them without having to download the whole thing. Okay, so we're going to load all of those. That's boilerplate stuff. Something about cross-validation, we'll have to make sure that model selection, we may need to go back and, so this was from a local version we were running in a previous year, so we'll have to go back and check this to make sure that this all works, in which the refactored classes and functions are moved. Okay, well, let's just go ahead and make that change here. So instead of cross-validate, let's make a new version of this. So we will, this used to say cross-validation. So we'll try this new version. Let's see if that helps. Okay, that looks like that helps. That sometimes you have to do that, and Python helps you understand when something was deprecated and is no longer available in the language. It is a living, breathing thing. Okay, so now we're going to use the pandas package and the function called read CSV to get our CSVs loaded up for this session. Now we're going to go ahead and look at the head and the tail. You've seen this before. Head and tail in a Python setting is a little bit different than in R. The head would typically be the function that goes out front in R, but in Python, because this is, I think, a little bit more intuitive with respect to the object orientation. You've got an object called a data frame, and inside it has methods that you can use to get certain evaluations to happen, and each of these different objects in Python have all these different methods associated with them. And so one of the methods that's associated with a data frame is the head, and you can put in the number of rows you want to see as part of the head. Same thing with the tail. Another method is shape. So if you just type the name of your data frame, .shape. One thing we need to be careful about in Python is names have underscores in them. They cannot have dots. The dots refer to drilling down and using a method inside an object. We could use the dots in R, but here in Python we need to use underscores in names, and the dots refer to the idea of drilling down and using a method. So here's a method called shape that just gives us the number of rows and the number of columns in our data frame. And here's our testing set that we loaded up, and we can look at the head and maybe take a look at the shape. So we have 6,493 rows and 9 columns. Why do we have fewer columns in the testing set compared to the 12 in the training set? That's because we don't have the realizations, the casual number of users, registered, and count, total of casual and registered users by by hour. So one of the things we can do is we can go ahead and create 3 new columns in our testing data frame. And to create a new column, rather than what you may have seen in R, which is $ and then the name of the column, you open up a square bracket and you just, in quotes, type the name of the new name for the column. And then here, this is we're going to use NumPy, and we're going to use the NaN method inside NumPy to give us a column of NAs for those. So now if we take a look at the head, we've got 12 columns, and we go out here and we've got not available or not a number entries here for those 3 columns, all the rows. Okay. Another thing that we may want to do is check out the data types. So a method for a data frame is a data type, and we see that our date time is an object, which is a generic description of a data type. It refers to something like text, and just like in R, we want this formally to be recognized as a date time data type. And so what we can do is take this column in the training set and in the testing set, the date time, and turn those formally to date time data types. And so we're going to use pandas, go in and grab the function called toDateTime, and transform or convert the date time column in the training set, and then similarly in the testing set to formal date time data types. So we do that, and then we go ahead and describe these things. Well, wait a second. Let's go to info, and now we can see, wait, it was up here. We were doing these D types, so let's just run that again. Now this is changed to a formal date time object. We can rerun these lines after having run the conversion, and it updates what types these are. So these are both now date time types. Another thing you can do is this describe method or function, which gives us summary statistics for any of our numeric variables. We can get info, which tells us how many of the entries of the total entries in the data frame are available and not missing. So that's everything. So we've got a complete data set. That's nice. We don't have to do much cleaning here. And we can do the same thing on the testing set, get the info, and we've got complete data except for all of this, which of course is missing because we're going to make forecasts for that. Alright, now we're going to engineer some features, and so what that means is we're going to add some new features to our data frame, extracting these features from the existing data set. So something we can do with our date time column is to extract the year that we're talking about. We can also extract the month that hour is in, or the which hour that hour is, or the day of week that hour is falling in. And we can do that for our training and our testing set. So we will go into this cell and go ahead and run this cell. One thing that's useful to know about how to work with descriptions of what's going on in a data frame, if we want to go beyond this notation right here, which is to refer to an entire column, these two highlighted chunks of code, that's a reference to an entire column. If we wanted to drill down to a particular cell, we would use this iloc method that's attached to the data frame object. And so this method or function can, like in R, open up square brackets and inside refer to rows and refer to columns. And so if you put a colon in, that refers to all the rows here because it's before the comma. And if you put a 0 afterwards, that's referring to the first element. And one of the important things in Python to remember is that Python numbers the first item in any list as 0, 0th item. That's really the first item. and then it labels the second item with a 1 and the third item with a 2, and so on. So when I run this line, I'm going to get the all the rows in the first column. So this is the date time column in the training data frame, all of the rows down to, and there are 10,886, and that's 10,885 in terms of Python labeling. And just to check the head here, we're going to go ahead and refer to, and you'll look up in this table to find this, but what we're trying to do is just convince ourselves that this iLoc thing works properly to get, say, the 4th row. So this is the 4th row, and the 12th column, which is here, this number 13. This is the 12th column, so we will put in 311 into our iLoc function and get out 13. Alright, so that's just a little bit of referencing particular cells or columns inside of a data frame using the iLoc function. Okay, now what we're going to do is continue on with setting up the training and testing set so that we can actually start fitting some machine learning algorithms. So out of this data frame, we are going to pick working day, temp, year, month, hour, and day of week. So we're just going to include these 6 independent variables in our training set. In the training set that we will actually let our machine learning algorithms try to learn from. So here we're taking the training set and just focusing on these 6 variables, and the Y for the training, this training set for the machine learning algorithms is going to be the count column. And similarly for the testing set, we're going to do it that way. And now what we're going to do to validate our algorithms internally here before we actually submit to the leaderboard on Kaggle, we're going to set up a validation set. And this validation set is going to be 25% of this entire original training set. And what this function does is it's nice. It allows you to write off the top with one line of code define 4 objects. And this train and test split is going to take the original X's in the training set and the Y's in the original training set and split it up 75-25 into these 4 sets. So 25% of the original X's is going to go into X train, 25% of the original X's is going to go into X valid, 75% of those Y's that are in this entire column will go here into Y train, and then the 25% will go into Y valid. And we're going to do this randomly with the random seed number 201. Okay, so we do that, and then we take a look at our head of these 2, and it looks like we've randomly mixed up the row numbers from the original training set. These are just row indexes that are behind the scenes in Python. So that gives us some indication that we've split that up well. Okay, now what we're going to do is define a function with the def syntax. We're going to call the function RMSLE, which is root mean squared logarithmic error. And this is the evaluation metric on Kaggle that you can go to here and read some more about. So we're back here, we're setting this function up. We're going to go ahead and clip predictions that might be below 0, truncate them to 0, and then we're going to put them into this function here, which is take the log of 1 plus the predictions minus the log of 1 plus the realizations, turn that into a NumPy array, go ahead and square it, and then take the mean, and then on the very outside after you've averaged, take the square root again and then return that value. Okay, so we're going to set that function up. Now we're going to fit a regression tree. So that'll be the basic building block that goes into the random forest and the boosted trees model. We're just doing this here for comparison purposes. We're going to use the function in sklearn called decision tree regressor sklearn calls a regression tree a decision tree. It's synonymous. And we are going to minimum samples split. That just means that there are 25 samples that are required in any node before it is split upon. If it has fewer than 25 points in a node at the end, it will not get split on again. And this is also a random, has a random component to it, and so we'll set the seed for that. We're going to go ahead and then pull in our smaller training sets X and Y to go ahead and fit this object now called RT, which is our decision tree regressor with these parameters set up. So when we use the method for this object, which is now a decision tree regressor, we're going to go ahead and fit and give it the arguments that go with the X and Y in the training set. And then when we want to go ahead and make predictors after this model has been fit, that's the name of the fitted model, the fitted model has a method called predict, and we just need to send to it the new x's, which is the x's in the which are the x's in the validation set, and then we can make some predictions that way. So let's go ahead and run this line, and now we will get this important thing out of any regression tree, which is our importance measures. So this is just a percentage of importance, so you can see that hour is the most important variable in this model, and we'll go ahead and just plot our predictions versus our realizations. So here's a prediction, here's the realization, at least in the validation set, and we can see how close we are to the 45-degree line. Gives us a visual sense for how accurate this model is. And here's a measure. We're 0.39 on our MSLE, the root mean squared logarithmic error. And if we go ahead over to leaderboard, just to get a sense for where that stands on the public leaderboard, let's see, you got to go down, got to load some more. Where is 39? Now, of course, this is part of the testing set here, so we're working with a validation set. No guarantee they're the same, but here we are in the 180s, 190s, maybe somewhere into the 200s, where something like this kind of RMSLE would fall. Okay, so now let's use the random forest regressor. It's going to take a few arguments: the number of trees we want in our random forest, the number of variables that are going to be considered randomly to be split on at each split in the tree, and then the minimum number of samples in each terminal node. And it's also going to have a random starting point, a random seed, so we're going to set that. So this will set up the random forest object. Then we're going to go ahead and fit that object to these data, the smaller training. And once we have that model fit, we're going to go ahead and use the predict method and put in the new x's. Okay, so go ahead and run that. And again, get out our feature importances. And you can see that again, hour is the most important. Temp was the next important at 12%. Let's contrast that for a second up here. Our second most important one was year in these these 6 variables. So it switched around a little bit under this other algorithm. And if we want to just take a look at, we've got some predictions down here that are pretty high, but with realizations quite low. So something is going on down here, at least on the low side, or I should say over prediction side, and might want to think about how to address that. So now we're going to look at how accurate this is. So this is a little bit more accurate, this random forest, than a single tree is. Not surprising, right? This is an ensemble method, and if you want to read some more about how it uses multiple trees to take advantage of the wisdom of crowds effect, that's discussed here in the introduction to statistical learning in chapter 8. Okay, next model, boosted trees model. and we're going to use the XGBoost package or the XGBoost algorithm to run a boosted trees model. It's a modern implementation of a boosted trees model. So what we're going to do is first set up our training and our validation sets. We need to put them into this special matrix form first. Inside the, this is our abbreviation for the package XGBoost. There's a function dmatrix, and it's going to convert our training X's and Y's into formats that XGBoost can use. Just a little bit of pre-processing that has to go on to use this algorithm. Then what we're going to do is we're going to use cross-validation coming up here to choose the best number of trees to include in our boosted trees model. Whereas that is something that, as long as you just get a big enough number here in the random forest, you're fine. 500 is a good number. Here in the boosted trees model, this is going to be a very important number to choose from doing some cross-validation. So see how well the model does out of sample on several validation sets, and then go ahead and several additional validation sets that are carved out of this smaller training set to see what is going to be the best number of trees to use in the boosted trees model. You can overfit a boosted trees model if you include too many trees in the model. It will just keep fitting itself to the errors that result, and eventually overfitting and picking up too much on the pattern or the noise that that's present in the errors. Let's see. So what are we going to set this thing to find out what? And so these other parameters can be tuned as well through cross-validation, but our main interest is in finding the number of trees. So we're going to set the maximum depth for each tree to 6. So these are pretty shallow trees, each of them. Our learning rate is how much is left over after each tree is fit, so it's really 1 minus this value, so we're learning at a pretty slow rate here. We're in a continuous variable setting, so we're going to use the reg linear objective, and it needs a setting of the initial seed. So we're going to go ahead and set up those parameters, and then through this XGB using the CV method, we're going to find out what is the optimal number of trees to use. So we need a few little arguments here. We're going to use 5 folds in this cross-validation, and we'll see what is the best number of trees. So when we hit this, off it goes. It starts fitting each tree. It already fit 20 of them, 30 of them, 50 of them, and so on. It's running them very quickly, and it's getting down to, let me get back to where that part of the report, there it is. We ran 500 total. That was the maximum number of rounds in this CV run. And you can see here that we started to come back up just near the very end. So 40, and this is RMSE, so this is 48.16, and we got down to some lower values, 48.0 something in here, lower values 48.07, somewhere around in the 400s. We got down to a lower value. So we'll go ahead and lower than going all the way up to 500. So we'll go ahead and put the number of rounds to 500 and actually train the model using the parameters we set up and the training set and the number of rounds we're now deciding upon, 400, from having done the cross-validation work. And then after we've got the model fit, XGB uses train instead of fit here. Once we've got it fit, then we'll use the predict method on the validation, the X's from the validation set, and make predictions using the boosted trees model. 400 trees, maximum depth 6, pretty slow learning rate from tree to tree. And then let's take a look at these important scores. And maybe the plot is easier to see, and you can see the ranking of the top 2. Now it's hour and temperature are the top 2. Hour and temperature, what did we have? We had hour and temperature were the top two, also under the random forest. Right, so now we're ready to do some visualization work. We've again got some pretty over forecasted hours, and when we look at the root mean squared logarithmic error, this model's not doing all that well. We need 2 more steps and we're home. We need to make predictions into the testing set once we've chosen which model we want to use. We'll go ahead and make predictions into the testing set with each of these models, and then we'll make some submissions, submission files, some CSVs that are ready to go and ready to upload onto Kaggle's site and get scored on their leaderboard. Okay, so how does this work? We need to retrain these models, and what we're going to do is we're going to fit the regression tree, we're going to fit the random forest, and we're going to remember XGBoost uses the word train to fit the model, and we're going to train these now on the whole training set, the original training set, the larger training set, not the smaller one we carved out so that we had a validation set. So once we retrain them, then we're going to use the predict method on the testing set, the X's in the testing set, and then we're going to go ahead and clip these so that we don't have any negative predictions. So a few of these models can produce negative predictions, so we'll just take the predictions, turn it into a pandas series, and use the clip function, or first use the clip function, then turn it into a pandas series, and then we'll have these clipped predictions that we can eventually put down here as the counts in the submission file. Okay, so we're going to run these line cell by cell. Have to do a little bit of pre-processing work again on the training and testing sets for XGBoost. That's the little work up front with these 2 additional lines. And then we read in the sample submission file. Oh, interesting. Okay, so the sample submission file is not here in this project yet. Let's go into this project and files and upload, and I'm going to go grab the sample submission file from Kaggle. The sample submission file is here. I'm dragging and dropping it there. Upload. It's uploaded. Now I'm back over here in the workbook. Let's see if I can connect to this. No, but I'm going to save this file, and I'm going to go to session. I'm going to stop and commit this. So I'm saving all these changes for now. I'll click OK. Okay, so they've been successfully synced. Now I'm back over here, and I'm going to go to the overview. No, I'm going to go back here, and my runs have been stopped. I'm going to go into bike sharing and look at files, and I see my sample submission now. I'm going to click on my notebook, launch the notebook, connecting again to a virtual machine on AWS. Here I'm back here, and I'm going to go ahead and restart and clear all the output. Okay, so I'm just going to quickly run down through all the cells one more time. This is something you occasionally have to do. The file's not available and you want to refresh the whole system. These algorithms are running quickly, so That's the cell that takes the most time to cross-validation on the boosted trees model. Okay, so now we're going to make our predictions into the testing set for those 3 models, and we're back to this point where we're going to try to load up. Great. So now the sample submission file loaded. We can take a look at the head of that. So that's just 0 counts, and we need to fill those in to make a submission file that's ready for Kaggle. And so we're going to just now create an RT submission, an RF submission, random forest submission, and an XGBoost submission. So just set up those data frames, and then add or change the column, the count column, so that we've got the clipped predictions from each of the 3 models in that count column. And then we're going to take that data frame. It has a method called toCSV, and we're going to write to these 3 CSV files. And let's do that. 1, 2, 3. We don't need this cell. And then let's go back here, and then let's look in files, and we do not see those results. So let's go back to this workbook. Let's save the workbook, session, stop and commit. Okay, so that killed the virtual machine, but we should have our changes saved in those CSV files saved. We're going to go into files again, and yes, I just clicked on files again, and now I see my submission files. So RT submission, RF submission, and here's our XGBoost. Any one of these files, you can just come over here, and you can download those, get them on your machine locally, and then go back over to let's see, where data, go back over here and make a submission, which is not hard to do. From the overview, of this, okay, I want to say we've got a link here somewhere to this. Let's go to the overview. Let's go back to this.